Good morning, Astronomy 1010. How are we today?
Good.
Yay.
Pretty good.
I've got some coffee here. I'm getting the caffeine that I need to instruct you in the ways of science. We've got a lecture on the second half of Celestial Coordinates today. We're going to review the horizon system. We're going to learn the Equatorial System. So we're going to do that for an hour and a half. Then we've got our lab. This is lab number 2 today. Lab number 2 is on the celestial sphere. It's kind of a fun lab, I think. Take some time during the course of your lecture today to hit print on, probably just need the first 2 pages, just the first 2 pages of lab 2. There's 4 pages in total, but I don't think we'll have time for all that. There's too many humans here. So get those printed at some point, or you may have to, if you don't have a printer, you're going to have your work cut out for you. You want to reproduce this table with a ruler, and reproduce this table. You don't need the text, but you need the tables. That's what we're going to be working on. So you can find that under the lab tab, of course, in Blackboard, okay? So we're going to start to, some words about homework, because I should say this before we get started. I graded all of those homeworks yesterday, and a few of the people who turned in labs late. The homework 1 and lab 1 are completely cut off. I had people who were trying to turn things in super late, and I let them get away with it for the first week. But it became clear to me that it's going to be really tough to handle grading all of your homeworks and labs each week for both courses. I will not be able to keep my mental sanity if I'm trying to do this week's work and previous week's work. So that Saturday cutoff, Sunday is when I do my grading, and anything that's in there, I will grade it. But after Sunday, I deactivate the homework and lab for that week, and I have no choice. This is like just a matter of survival on my end. So I hope you guys will take that serious. Another thing that I saw a few times that gave me the willies was people who were sort of typing up their answers, and all they really did is they kind of wrote down just the answer to the problem. When you work on a problem set like the homework that we did on Wednesday, it's about the process and showing all the work. Let me make this message simpler and stupider so that people don't misconfuse me. Whatever I write down on the board, that's what you write down, okay? You have to write down whatever I write down. If you have anything else than that, if you get creative, I will punish you, okay? Creativity is bad. You just want to do exactly what I'm telling you to do until you've learned better, okay? So please, if I show a calculation, if I put units in there, if I show a process, I need you guys to do that too, okay? Most people did do that just instinctually, but having seen a couple of wee-woos, I need to make sure I've talked about this, right? Okay, all right, so much for that. If there are no other comments or questions about this, then we are going to get right into it with a little share screen here. And I'm gonna call up a slide, I think it's slide 47. Let's see what happens here. Boom, boom. Oops, that's 46, there's 47, okay. How good am I? This is a 3-dimensional picture of what is called your local sky. Your local sky is the real dome, the sky that you see when you step out at night and look up at the heavens. You could be standing in a grassy field or on a desert, but we're going to ignore any potential buildings or trees that could be blocking the view. Probably the best way to see a complete local sky would be to be on a boat with very calm water. There will be no obstructions on your horizon, and the sky will truly be a hemisphere, half of a sphere. We are looking for ways to talk intelligently about the motion of objects through our local sky. From a location like Rhode Island's local sky, the path that stars take through your local sky look a little something like this picture here. This picture shows circles known as star tracks, or if you want to use some fancy vocabulary words, you would call them diurnal circles, the path of the stars over the course of the night. And we want to build up our muscles, our brain muscles, so that we can talk about the paths that stars make as they go through these stars. Whoa, I'm checking out Andy's Zoom here, and I like the fact that his class is literally moving 60 miles an hour down the highway. That's pretty cool, Andy. I hope you'll be able to understand all this while driving on the highway, but hey, it makes for good background anyways. So back to slide 47, one of the ways we learned how to describe the position of stars in our local sky was by using, something called the, oh Jesus, here I go, the horizon system. And the horizon system was a simple way of describing the position of a star using altitude and azimuth. Altitude is degrees above the horizon. Azimuth is degrees along the horizon. Let's start off today by doing a little diagram, and we're going to make a two-dimensional view of our local sky to review what we've learned. This is also a good diagram to know how to make because it can help you during the test when you're doing tricky problems. Just a moment, guys. You can't see it, but I've got a little streaky here. I need to... All right, so let's call this section of our notes a 2D view of the local sky. And this will be for an observer like Providence, Rhode Island. Start by leaving yourself a good amount of headroom. Just like we did the other day, we are going to take a ruler. You guys might have a clear plastic ruler somewhere. I recommend you make your line about 12 centimeters on the page if you have access to a ruler. I'm going to make mine a little longer than that because I'm on the board here. Make mine 60. Make your line 12 centimeters long. Find the midpoint at 6 centimeters and go ahead and make a dot there. And then I want you to draw a line that's 6 centimeters tall, perpendicular to that. Okay. We're going to try to make a dome, so I'm going to mark out a few of the points here. I'm going to mark out 6 centimeters as a couple of dots in various directions from the center. This will help me make a decent dome. I'll be able to just simply connect the dots. Someone might want to mute themselves. I can hear you. I don't know what you're doing, eating Cheerios or something. There you go. I made a few dots so that I can make a nice dome here. Hey, while I'm at it, I'm going to take off this chime that, hold on a second here, manage participants. Get rid of the chat. Play the sound. Okay. There was a little ding that was happening every time someone joined the party here, so I had to get rid of that. All right, let's go ahead and draw the best dome that we can draw with our free hand. Notice those dots help us make a nice two-dimensional view of the local sky. Remember that we always want to choose, yes, Heva, I suggested that because that would probably fit in a standard notebook pretty decently. If your notebook is small, you might want to make it a little shorter than that. The exact dimensions don't matter, Heva, as long as you try to draw it well. If you have a protractor, you could even just trace your protractor quickly. That's another cute trick. Okay, sorry, I need some coffee here. All right, it's always, hold on. Someone doesn't know how to mute themselves, so I'm gonna find you and manually mute you. Is that Andy? Who doesn't know how to hit mute? Okay, there we go. Back to speaker view. Now it's important that we choose north and south, okay? Let's put north here. And let's put south on the left-hand side. Let's shade in the ground a little bit. This is a two-dimensional view, but it doesn't mean we can't make it jazzy. All right, let's put an observer dude in the center of the field. This is a Rhode Island local sky. So we should be able to see the north celestial pole and the celestial equator there. I'm going to put in the north celestial pole, drawing a blue line that goes up to the north somewhere from the foot of the observer. Let's label that NCP for North Celestial Pole. And of course, you guys may remember that there's a famous star there. The North Star Polaris is located on the sky at the North Celestial Pole. Stars that are on your sky have to be on this dome. They can't be outside of that dome, okay? Now, if we want to draw the celestial equator, we have a wee bit of a problem. The celestial equator is an east to west phenomenon, as slide 47 will demonstrate. So we can't draw in the entire celestial equator, but what we could do is we could try to draw in the line that goes up to the celestial equator, and we could draw the point where the celestial equator intersects our meridian. I'm going to be using some fancy vocabulary terms today, so I do hope you can keep up with me. I do hope you understand. What's the meridian, class? Someone enlighten me. Prove that you understand what I'm talking about. Can anyone tell me what the meridian is? I thought you were in a group of enlightened students, and now I'm beginning to have doubts.
An arc that rises due north.
Keep going, Matt. I like it.
Reaches due zenith and sets due south.
Beautifully said. Okay. So in other words, Matt's saying it's an arc that starts due north. It's the line that cuts your sky in half, north to south. It's this arc here. So we're going to draw where the intersection of the celestial equator crosses your meridian, in other words. In fact, that's what we just drew in here. We're doing a north to south slice. So this arc that you just drew in is your meridian. Okay, let's draw in our celestial equator. We'll keep it perpendicular to the north celestial pole. And I'm going to just use a dash line here. And I'm going to put a dot, and I'm going to label that CE for celestial equator. Now, this is the first time that you guys have done this drawing, so I did it kind of slow and careful so that I was sure that you were following along. But you can make this diagram quickly and hastily, and it will help you think your way through difficult problems on the test. Today, we're going to play a game. And the way we're going to play this game is we're going to label 4 angles on this diagram. Hold on while I find my green marker here. I'm going to label 1, 2, 3, 4 angles using the first 4 letters of the Greek alphabet. Ooh. Green marker's dead. That's bad. Oh, here's another one. Alpha looks like a little Jesus fish. Beta looks like a squiggly B. Gamma looks like a squiggly Y. And delta looks like a squiggly D. All right? Alpha, beta, gamma, delta. 4 angles. Now, class, one of these angles, alpha, beta, gamma, delta, is a direct representation of your latitude on Earth, based off the definition of latitude. Can anyone out there in the studio audience guess which angle represents your latitude? Alpha, beta, gamma, delta. Matt, you were helpful at reading things. Before someone answers, maybe you could read the definition of latitude as a sort of inspiration. And then Alex, if you want to guess or whatever, anyone can guess. Meanwhile, I'll improve the way my beta looks. That's a better beta. Okay, Matt, what did you learn?
I'm not finding the definition exactly.
Did we not do geographic coordinates last time?
I think we did, but I'm having a hard time.
Jake?
I have
Jake,
Okay.
hit us one time.
degrees north or south of equator.
Okay, so which of these angles, anyone at all, might represent your latitude?
I'm guessing delta.
Who said that?
Nicole.
Nicole, here's the thing, Nicole. I got to tell you something complicated. It's not that you're wrong. It's just that you're not right, okay?
Okay.
Alpha?
Pardon?
Wouldn't any of them be?
Wouldn't it be alpha if it's not delta then? Oh, then it's, I already know what
In order
it is.
to understand what's going on here, guys, it might be helpful for me to draw an Earth underneath you. So just humor me for a second here. I'm going to draw an Earth using this Frisbee, and I'm going to get you to look at this problem in a new way. I'm going to draw Earth with Earth tilted in the same direction as that north celestial pole, right? So here's my circle. So let's say I draw Earth, and then in the same direction, I draw the North Pole, like so. So this is the North Pole of Earth. And then I draw the equator perpendicular to that. Okay? Ooh, I didn't really do a good job of this here. Hold on a second. The North Pole and the equator have to be in the same direction as the sky for this diagram to work. So bear with me. That equator looks better. Make it parallel. There's your North Pole. And now let me put an observer here. I don't know if this helps you here. How did we define latitude again, Jake?
Latitude is degrees north or south of the equator.
So Jake, if this is the equator, your degrees north of the equator would be like that, right? That's your latitude.
Correct.
So which angle represents your latitude on the sky?
Beta.
That's right, because the equator points in the direction of the celestial equator. The North Pole points in the direction of the North Celestial Pole, and your head points in the direction of the zenith. Your feet and your zenith, as long as you're not a hunchback, your feet and the zenith are the same direction, right? So if the angle between the equator and your feet is latitude, the angle between the celestial equator and the zenith is your latitude, or otherwise beta is your latitude. Very good. All right, let's try another guessing game. One of these angles represents the altitude of Polaris based off the definition of altitude. Which of these angles represents the altitude of Polaris? What does altitude even mean?
Altitude is degrees above the nearest horizon. So, for example, the zenith is at 90 degrees.
Okay, good. I like what you're saying there. So which of these angles would represent the altitude of Polaris?
Delta.
Very good. Delta is the altitude because, as you guys can see, this is your nearest horizon here. That's the ground, but that's your northern horizon right there. And if delta is the angle between the horizon and Polaris, then that is the altitude of Polaris. Now, let's do this for the Rhode Island local sky, okay? Remember, this is a 2D view of the Rhode Island local sky. Do you guys remember what the latitude is for Rhode Island?
Wasn't it 42 degrees north, roughly?
Good. So this angle is 42 degrees. Now, I spy with my little eye a 90-degree angle between the north celestial pole and the celestial equator. That makes sense. So what should gamma be then?
48.
Very good. Because they have to add up to 90 degrees. And now, I spy with my little eye another 90-degree angle. The zenith and the horizon must always be at a 90-degree angle, which means what about delta?
42.
Yeah, delta is 42 degrees. For completeness, we could fill in alpha. You guys know what alpha is, right? What's alpha?
48.
Okay, all right, just check. Make sure we're not crazy here. Now, what's interesting is 42, 48, 42, 48. We did that for the Rhode Island local sky, right? But in general, it's always going to be true that this is a 90-degree angle, and it's always going to be true that that's a 90-degree angle no matter where you go on Earth. Therefore, we have just proved a fundamental result, which is extremely important in astronomy. I'm going to write it down underneath here. The result that we've proven is that the altitude of Polaris is equal to your latitude. And that is a fundamental result of great importance. Put a box around it, put some stars next to it, hell, put some fire beams coming off it so that you can find it at a later point when you're looking in your notes. You can solve many problems based on the altitude of Polaris is equal to your latitude. In a way, this is the basis of all of celestial navigation. This is how you find your way around the ocean when you're lost at sea. Lost at sea will be one of our homework problems this week. You'll have to use this for that. Okay, this was your first attempt at using the horizon system. Let's try a few sample problems that are going to come right out of our homework this Wednesday. So we're actually going to pre-game couple of our homework problems just so you can see how we could use these results, okay? I need to erase. Does anyone need a little more time on the diagram? No one needs more time? Okay, I'm erasing then. Let's try this as a question. Describe the location of Polaris in the Rhode Island local sky. Does anyone know how to do this? How do I do that? No? Did anyone just not learn what we just taught? I taught you just a second ago? I thought you might be able to use the thing I taught you 15 seconds ago to answer that question.
Do you want to find your altitude right now?
Hold on. Unless I've been smoking doobies or unless I'm taking a hot air balloon ride, my altitude is 0 because I'm on the fucking ground, okay? Like, it describes authenticity a little bit, but unless you're high, you don't have an altitude, okay? Stars can have an altitude because they're on the sky, but I am on the ground. Do you mean my latitude or did you mean something else?
I meant latitude.
Okay. Well, we know our latitude, don't we? Because I specified in the question that it's the Rhode Island local sky. And you guys know the latitude of Rhode Island, don't you? It's 42 degrees north. Okay. You know what? It's okay that you don't know how to answer this. I kind of figured you wouldn't know how to answer this. I kind of figured you wouldn't know how to. Oh, sorry. Anyone?
Sorry, I didn't know if, since it's the local sky, do you have to use the horizon system to like
Oh my
describe it?
Who said that? Who said that? I like you. Who are you?
Noah.
Noah, you're a goddamn genius. I couldn't have said it better myself. That's the whole point of this problem. You need to use the horizon system because this is in your local sky. You understand me. Somebody understands me. Let's write that down. We have to use the horizon system. And what two angles does the horizon system use? This is the point that I'm trying to make. Noah, while you're at it, what are the two angles?
It's the degrees above the nearest horizon.
What are their names?
Is that altitude? I don't.
That's one of the angles. What's the other one?
And then azimuth.
Good. In other words, Noah, what I'm looking for in this question is I want an altitude and I want an azimuth. I want two numbers.
So would 42 degrees be the altitude?
Hell yeah, because you just learned that the altitude of Polaris is equal to your latitude. Very good. What about the azimuth?
Is that 0 since it's just going to be north?
That's right. This is kind of like what color is an orange or who's buried in Grant's tomb. The North Star is located north. Now, the technical azimuth of north is 0 degrees, but sometimes we can actually just use north, south, east, west in place of azimuth. So the way you would describe Polaris in your local sky, you'd say it's at an altitude of 42 degrees at an azimuth of north, which is 0 degrees. Now, Heva, this might sound hard at first, but once it clicks in your brain, it's easy, okay? Everything is hard until you understand it, you know, like multiplication is hard. And then one day comes where you know your times tables and it's not a big deal anymore. Okay, Noah, while you're at it, because you're so damn good, why don't I let you draw on the screen here? Did I give you permission? Allow students to rename themselves. Allow students to share screen. I think you can draw on this. Noah.
I'm pretty sure. Yeah.
Well, I guess it won't be that hard to point to where Polaris is because what you would do is you'd start north. I was going to have you draw where Polaris is, but it's, oh yeah, is that you? Go ahead. Make a,
Yeah, I did that by accident.
that's okay. Circle Polaris. This is kind of helpful because you guys can all draw on this sometimes. Circle Polaris. Yeah, exactly. You look north, you go up 42 degrees, and there it is. Okay. By the way, while we're annotate, let me clear all the drawings for a second. While we're doing that, remember that Polaris can be found in your local sky, and I challenge you to find Polaris on your own. If you don't know where north is, if you don't have a compass tool, hold on a second. I know the picture's here. I just can't remember where in damn hell I put it. Oh, where's my Polaris? Where's my Polaris? Huh. It should be. Okay, this must be a little further along. There we go. Sorry. Slide 80. I probably mentioned this before, but it never hurts to repeat myself. If you want to find Polaris on your own, you can either look for north using your compass tool on your iPhone and then go up about halfway through the sky. A simpler way to do it is to find the Big Dipper and to use the pointer stars. The front two stars in the Big Dipper are called the pointer stars because if you make a line through these stars, they point kind of close to Polaris. Polaris is not the brightest star in the sky. It's just a medium brightness star. But if you use the pointer stars, it should be pretty obvious which one is Polaris because there's no other bright stars nearby. Polaris is also the handle of the Little Dipper. But as I've mentioned before, these stars in the Little Dipper are really faint. You might be able to see them from Charleston if you go down to the observatory there on a Saturday night. But you usually can only see Polaris, and you can see Kochab and sometimes this star. So it's kind of hard to make out the Little Dipper. The Big Dipper, on the other hand, is very bright. So that's why these two stars will help you find Polaris. Okay, remember that during the course of the night, if we point a camera towards Polaris and we take a long exposure photograph, as Earth spins, we will see stars actually rotating around Polaris. And we have a special name for those stars which are so close to Polaris in the sky that they don't actually go below the horizon. These are called circumpolar stars. A definition of circumpolar stars is that they never rise or set. This is kind of an awkward place to put the definition, but let's go ahead and do it anyways. Circumpolar stars never rise or set because they're so close to Polaris. You can think of the Big Dipper as almost a circumpolar constellation in Rhode Island's local sky. Unless there are trees blocking your way, no matter what time of the year you're in, at some point in the night, you can usually see a portion of the Big Dipper. Polaris and Ursa Minor, of course, are totally circumpolar. You just have to be in a dark enough sky to see them. That was a good exercise. Let's try one more question. Let's try a harder question. And these are all right from our homeworks this week. Question 2. Describe the path of the celestial equator in the Rhode Island local sky. This is another very good exercise for us to try. I don't suppose anyone's brave enough. This one might be a little outside. Oh, the last line, you mean the circumpolar stars, Heva? Is that what you mean? Here, I'll do it. I should always ask you guys. That's the quick and dirty version. Guys, let's just take a peek at that slideshow again. Let's go to slide 47. I'm asking you to describe the path of this thing in your local sky. This is a more complicated question because Polaris was just a single point on your sky. But this is not a point, it's an arc. And to describe the path of an arc through your three-dimensional sky, you probably want to choose 3 points to do it. The points that you would like to choose are the point. Oh, I'm sorry, Andrew?
I know. It's going to be east and west.
Well, Andrew, that's the right idea, but your answer is not sufficient, and let me explain why. To describe an arc properly, but stay tuned, we're going to want your help, okay? To describe an arc properly, you need 3 points. The point where it rises, the point where it reaches its highest, and the point where it sets. But each of those points can only be described using the horizon system. In other words, we're going to need an altitude and an azimuth for each point to do this job right. Let's try to write this down. We're going to want an altitude and we're going to want an azimuth for 3 points. The point where it rises, the point where it reaches, and the point where it sets. I call it the rise, the reach, and the set. And they're each going to have their own altitude and azimuth. So let's start with the rise point. If you ask me, I would say, annotate tool. I would say that this is your rise point right there. Can anyone describe that point, altitude and azimuth?
Would that be altitude 0?
Yes, because it's on your horizon. Very good. Nice. The altitude is 0. What about the azimuth?
Would that be 0 east?
Hold on. The east part was correct. The 0 part is not correct because remember that azimuth measures degrees along the horizon measured clockwise from north. So do you want to revise your answer?
So it'd be 90?
Very good. 90 degrees or east, either one would be fine.
Okay.
And that's the same as due east for the record. How about the reach?
Right.
This is the reach here.
Would that be 48 degrees?
Nice. How did you know that? Who said that and how'd you know it?
It's Christian, and it's 48 degrees from south, that horizon.
Yeah, because we just learned that in the alpha, beta, gamma, delta game, right?
Yeah.
Man, I'm really digging Andy's Zoom video here. I feel like I'm going on a journey. I feel like I'm not stuck in my apartment at work, but I'm going on a long road trip. Okay, so 48 degrees, and what did you have for your azimuth?
180 or south.
Beautiful. You, Christian, understands the horizon system. So that's 48 degrees. And that's 180 degrees or south. And someone else can do the set.
Oh, wait. I think I got the other one.
All right, hit me.
I got the azimuth. What is it?
You want some visual help?
Oh, 240 west.
That's the azimuth, right?
Yeah, that's
It's not 240, by the way. It's 90. 180 plus 90 is 270, right?
Oh, all right, all right.
So to go from here all the way around, that's 270 degrees. That's your unit circle. What about the altitude of that point?
Would it be 42?
No. Altitude is degrees above the nearest horizon. How many degrees above the horizon is the yellow dot? Anyone?
0.
Yeah, it's on the horizon. So it is no degrees above the horizon. Good. Okay. So the altitude is 0 degrees, 270 degrees, or west, which is due west. Now, if you wanted to say this in a kind of literary way, let's say you were an English major and you don't like all these damn numbers, Brendan. Why are you always impressing me with your technological number mumbo jumbo? I just want to like talk about bees and poetry and stuff. Okay, well, you can actually do that and still sound like you know what the hell you're talking about. In a literary way, you could say the celestial equator is an arc that rises due east, reaches 48 degrees in the south, and sets due west. That's a kind of classy way to answer that question that contains all the specificity of the horizon system. That is a clear statement that is not ambiguous and correctly describes the path of the celestial equator. So even though I wanted you guys to do it in a table format with some numbers, you could have actually said that in a kind of more elegant way if you wanted to. Just trying to show you there's a couple of different ways to skin this rabbit here. Just giving you guys a second to finish writing. Adam, give me a thumbs up when you're done writing. All right. Anyone else need a moment here? Or are we good? I'm gonna rate.
Can I have a moment?
Oh yeah, sure.
Sorry.
That's okay. Can you just let me know when you're done?
Sure.
In a moment, I'll show you how we can use the horizon system in a telescope. This is a crappy telescope, and crappy telescopes, actually some good telescopes use the horizon system too. This is called an altitude azimuth mount, and I can raise or lower my telescope in altitude, okay? I can swivel in azimuth, that's the azimuth direction. You still writing?
I just finished.
Cool.
Yeah.
Let's show you guys a telescope that I would, a better telescope, one that would really get me excited about life. I would love to own a plane wave 1 meter telescope. This is a gourmet. This is a gourmet telescope making company, and they make some very large telescopes. A 1 meter telescope is like pretty insane. I wonder if I could find, where's their, oops, sorry. Let's go back to their homepage. Let's see their fanciest telescopes here. I had one for a sec. Oh, here we go. Yeah. So look, a plane wave 1 meter telescope, or this is the 0.7 meter, only costs $250,000. Not too expensive as far as telescopes go. I would sure like someone to buy this for me for Christmas. If you have any rich friends or relatives that are looking to spoil your astronomy professor rotten, just let me know. And this fancy telescope, which you can do serious astronomy research in, it operates on an altitude azimuth mount. Let's see if we click on, oh yeah, look at this. So here you can see the telescope swiveling in azimuth, and those fork arms, they up, down, lower it on altitude. So you can do all sorts of cool things with this telescope. Like you can go out and you can look at the Orion Nebula with your Grammy. And if you go out to the telescope with your Grammy, you could say, Grammy, I need you to point the 1 meter telescope at the Orion Nebula. Your Grammy's going to say, I don't know where the Orion Nebula is. So that's easy, Grammy. It's at an altitude of 30 degrees due east. So Grammy points the telescope, she swivels it in azimuth to east, and then goes and points up to the Orion Nebula. Now, here's the difficulty with the Horizon System. As you know, stars are constantly rising and traveling through the sky. So what's irritating is if you use a simple telescope like this and you spend all this time getting the Orion Nebula into focus, as soon as you step away from it and say, hey, Bob, come over here and take a look at this thing, by the time they look at it, it's already rotated out of the field of view. That's not a big deal because modern computers can track the motion through the sky, and they make small adjustments in altitude and azimuth. In fact, while we're sharing here, let's do plane wave 1 meter telescope. And they've got a cool YouTube video. Let's see here.
Why is it so much money?
Because, all right, first of all, because it has a giant ass mirror in it that someone needs to polish to a very precise shape to like a fraction, a fraction of the wavelength of optical light. So you need a very precisely polished mirror, and it is a masterpiece of engineering. It may not be obvious to you guys just how big this thing is. It's massive. And
Santa might give it to you.
huh?
Santa might give it to you if you ask him.
I keep
If I get it to you, can I get an A in the class?
You know what? I'm just about thinking it would be a worthwhile trade. Okay, hold on. I want to show you this YouTube video. I think that's kind of how this is how it works. Oh, here we go. This is the video. You do get A's in life if you buy your professor's $500,000 telescopes. They put your name on it. I won't just give you an A. I'll put your name on the building and I'll build a statue in your honor, and you shall be known forever as the woman who saved astronomy at CCRI. Okay, so I think if everybody else can do it, then so can I. Here, that's
a deal.
All right, this is a picture here of this thing slewing in the clean room here, or here. Sorry, this is their warehouse, and they're just sort of testing out its functions. You can see they're sort of slewing it around with the computer. With a telescope like this, CCRI students could do professional grade research and publish papers in serious magazines. That would make you a shoo-in for transfers to fancy schools like Yale and Harvard. So it would be a cool thing to have something like this at our disposal. We have a nice telescope, a 16-inch telescope, but this is a whole different level of crazy. This is a whole different level of crazy. This is a telescope you do professional grade research on. So we got a couple of problems. The first is that the nighttime sky is constantly rotating, so we have to keep adjusting the mount. The second problem is, what if you discover something, right? Nicole, what if you discover a nebula for the first time and you say, I want to call this the Nicole Nebula, and everyone from now on will refer to this nebula by my name because I'm Nicole and I found it. You could find it in your sky and say, everyone, I found it at 30 degrees altitude in a direction east. But if you start calling your friends in other countries, like if you call someone in, it doesn't even have to be in another country. What if you call someone in Florida? Say, I discovered the Nicole Nebula, and I'm going to tell you where it is. It's at an altitude of, wait a minute. If it's at an altitude of 30 degrees east in Rhode Island, that does not mean it's going to have an altitude of 30 degrees east in Florida, because we just learned the altitude of Polaris is equal to your latitude. If you go north or south on the Earth, the positions of stars, they shift. What we need is another coordinate system, a professional grade coordinate system, which will be stuck to the celestial sphere itself, so that once we discover new stars and galaxies, they will keep fixed positions. In other words, the horizon system is nice for just pointing to things in your local sky, but if we want to have a professional astronomy organization, it might be nice for us to have a set of coordinates that are kind of like latitude and longitude for the celestial sphere itself. And that's where the equatorial system comes in. It's a set of coordinates that are like latitude and longitude for the sky, and they stay stuck to the celestial sphere. We're going to need to introduce them carefully, okay? Okay. So let's introduce the equatorial system. You need this for your lab today. The equatorial system, oh, sorry. There's some music playing in the background. Shoot. I was watching this this rock video last night, and it kind of came up after my YouTube ended. The equatorial system. Okay, the equatorial system uses two angles, which are like latitude and longitude for the sky. They are called declination and right ascension. Usually astronomers abbreviate them as dec and RA. That's how people usually talk about these coordinates here. I'm going to do something a little weird. I'm going to try to show you what declination and right ascension look like before I define them. I'm always trying to find new ways to enlighten you guys about stars. Let's look at a star like Sirius, the star. And let's go to the Wikipedia page where they'll have its coordinates, its right ascension and declination. And here you can see, guys, the declination is minus 16 degrees, okay? But notice the right ascension is displayed in a weird format, 6 hours and 45 minutes. Okay. Declination is the equivalent of latitude on the sky. It's kind of like latitude. And right ascension is kind of like longitude on the sky. Now, the declination is based on the celestial equator. So the declination is defined as the degrees of a star, positive or negative, from the celestial equator. In other words, here's my sky. The seam of the globe here is my celestial equator. And if I go up from the celestial equator, positive 10 degrees, positive 20, positive 30, positive 40. If I go down, negative 10, negative 20, negative 30, okay? The right ascension, the longitude lines are like this. They kind of run like tangerine slices, and they go through the globe from north to south. They measure east to west. And instead of measuring in degrees, they measure in hours. We're going to talk about that. One of the reasons why, do you guys remember how we defined longitude on Earth? How do we define longitude? How do we do it on Earth?
Isn't it degrees east or west from the prime meridian?
Exactly. Now, we're not going to be able to use the prime meridian for celestial longitude or right ascension. And you can see that the Earth rotates with respect to the globe. So the prime meridian keeps twisting during a 24-hour day. You want to have something that's actually stuck to the globe itself. It turns out that the point we're going to use to be the equivalent of the prime meridian is the point called the Spring Equinox. And here I might want to give you guys a picture to show you what's going on. Remember that the Earth projected onto the sky projects a north celestial pole, a south celestial pole, and the red line here represents the celestial equator. The purple line represents the ecliptic. The ecliptic is the path that the sun makes against the background stars over the course of 1 year. So this is the path that the sun is making as it drifts through the constellations of the zodiac. The spring equinox can be thought of not only as a day of the year, but it also can be thought of as the point where the celestial equator meets the ecliptic. And I'll do a little bit on the spring equinox in a second. But for now, I'll just tell you that this point, the spring equinox, where the celestial equator meets the ecliptic, that's going to be the 0 point of right ascension. And we're going to measure only eastward. Eastward is counterclockwise along the celestial equator as seen from north. Okay, here's the definition of right ascension. It is the hours, minutes of a star measured eastward from the spring equinox. For instance, let's take a famous star like Vega. This is in your homework. There's a famous star that's up in your nighttime sky during the summer called Vega. It has a declination of positive 38 degrees. And I think its right ascension is 18 hours and 15 minutes. No, sorry. 18 hours and 35 minutes. That's how you write right ascensions and declinations, just like that. I thought I would take a moment to explain why we measure things in hours, and then I want to take a moment to talk a little more about the spring equinox. Then we'll do some sample problems. For now, I just wanted to get those definitions into your notebook. Let me know when you're all set. Oh, I guess you can't do that. There's too many of you. Does anyone object to me erasing, or do you need another minute?
Can I have a second? I'm sorry. Okay, I'm all set.
Okay. I'm going to erase here. So let's talk about why we measure right ascension in hours rather than doing it in degrees. You might want your Casio calculator for this. So here's the Earth, right? And the Earth spins in a single day. It rotates through 360 degrees, and it spins through this 360 degrees in 24 hours. Why don't you guys divide 360 by 24 on your calculator and tell me what you get?
I got 0.
That doesn't make sense, right?
At 15.
Oh,
Kevin
15.
got 15, a few others did as well.
Yeah.
And that's, watch my units, that's okay, 15 degrees per hour. It's not a coincidence that that number divided so cleanly. That's thanks to the Babylonians, who invented the hour as a 15-degree wedge of the sky. This was intentionally done this way. Okay, this goes back to Babylonian astronomy. And it means that there's this weird conversion factor that makes sense in astronomy that normally wouldn't make sense. And it goes like this. 1 hour is equal to 15 degrees of sky rotation. So we could measure the rotation of the sky in degrees, or we could measure the rotation of the sky in hours. Since the sky is constantly moving, it turns out to make a little more sense for us to measure the rotation of the sky in hours and to measure the coordinates of stars in hours as well. In your next class, you're going to learn about local sidereal time. And that's when you'll start to understand why we bothered to measure right ascension in hours. So if I wanted, I could measure the coordinate of a star along the celestial equator. I could measure it in degrees, but it turns out to be more useful to measure it in hours. Okay, now I've explained why hours and degrees are the same thing. We can even use this to convert. Put a box around this. This will come in handy at some point. I promise you that. Let me just give a second for you guys to catch up to me because I know there's a little lag there. Okay, I'm going to erase. Let's also take a moment to talk about the spring equinox. The spring equinox is the point that we chose to start measuring right ascension. And I think this is as good a time as any to slow time down for a second and to tell you that the spring equinox can mean many different things depending on the context. The spring equinox is 4 things at once, okay? First, it's a point in Earth's orbit. That's how we originally introduced the spring equinox. We told you that the Earth, as it spins around the sun, right? Let's see, coming out of the winter solstice here. As Earth rotates around the sun, the exact moment of the spring equinox is the moment where the equator, let's see, I want to make your camera the sun, okay? It's that moment when the equator points most directly towards the sun. A moment before, a moment after, the equator does not point as perfectly towards the sun as it does right here at the spring equinox. So that's the spring equinox, the exact moment. You'll notice that the axis tilt of Earth makes a 90-degree angle with respect to the sun, which is U. So we started off by defining the spring equinox as a point in Earth's orbit. It's also a day of the year. And the day is usually around March 21st. Here's a third concept. The spring equinox is also a point on the sky. And this is what sense we're using it for. It's a point on your local sky. It's the point where the celestial equator intersects the ecliptic. In fact, let me show you another picture here. The spring equinox is actually a location on your sky. It's just it's a random dot located somewhere below the constellation Pisces, right about there. Okay? And every day, this dot will rise in the east and come up through your sky, cross your meridian, and then it will set down in the west. Okay? You've probably never noticed the spring equinox before because there's nothing there. It's just an empty point on the sky. Most of the time, anyways. Actually, it turns out that one day per year, on a very particular day, a special astronomical object will appear at the spring equinox once per year. Anyone think they could guess what that special astronomical object is that appears at the spring equinox for just one day each year? A special astronomical...
Would it be the sun?
Oh, who said that? Who said that?
Christian?
Christian, damn it, why you gotta raise the bar so high? That's right. And guess what day the sun will be there, Christian?
Around March 21st?
Exactly. And let me tell you where the sun's gonna be in June 21st. It's gonna be at the foot of Gemini. And in September 21st, which we're headed towards, it'll be in Virgo. And in December 21st, it'll be in Sagittarius. That's what these points mean. They're showing you where the sun is going to be. And we can use this as a point on which to base our right ascension. The final thing that's confusing is the spring equinox is also a moment in time. That's because the Earth is constantly moving during the course of a day. So it's easier to see this with the summer solstice, but even during the summer solstice, the Earth moves a tiny bit in its day. There's some point during that day where the North Pole is perfectly lined up towards the sun. That's the moment of the summer solstice, of the spring equinox. Because of this ambiguity, you can end up seeing some rather goofy questions on an astronomy exam that sound crazy, like, what's the location of the spring equinox at noon on the spring equinox? Ugh, that would be a confusing question to answer. Describe the location of the spring equinox at noon on the spring equinox. That'd be confusing, wouldn't it? Okay, hopefully you won't get any questions like that on your test. Who knows? Let's try a few examples. Okay, so here's some food for thought. If these points are points on our sky, they're points in the celestial sphere, each of these points should have a unique right ascension and declination. Let's practice the equatorial system by trying to figure out what the coordinates of those points are, okay? So this is a sample problem. So we're going to, so I'm going to stick to blue because my black markers are dying here. Find the equatorial coordinates of the 4 key points on the celestial sphere. So we'll start with the the spring equinox. We have a right ascension and we have a declination. So let's start with the right ascension and declination here. What do you think? Can anyone guess one of the coordinates?
0 degrees.
Which coordinate are you giving me, Joel? You got to know which one you're giving me here.
The latitude.
Equatorial coordinates use right ascension and declination.
Oh,
So-
declination.
Declination. Okay, correct. Your declination is 0 degrees. That's fair. Its declination is positive or minus from the celestial equator. How about the right ascension?
Would that be 0 hours?
Very good, because it's on the spring equinox. The way you write it is you write it like a military clock. 0, 0, colon 0. 0 hours and 0 minutes, all right?
Well, technically, there's no colon in there if it's military, but sure.
Oh, okay. Let's say a 24-hour digital clock. So, and due respect, actually, I don't know how they do Zulu time, as you guys call it.
Yeah, it's
So-
just 4 numbers.
Say that?
It's just 4 numbers.
Okay, like 1801, 1805, something like that. Okay, that's cool.
Yeah.
Usually in right ascensions, you put a colon in. Summer solstice. Let's kick it up a notch. Right ascension and declination. Show you the picture. Can anyone give me one of those two coordinates here?
90 degrees.
Hold on, which one are you giving me?
Declination.
No. Declination is measured positive or minus from the celestial equator. And I would assert to you that this angle, this is your degrees above this, that's not 90 degrees.
True.
You want to try again?
42.
No.
I'm just throwing out numbers, so.
Okay.
48.
Not
Oh, wait, is it? All right. I know that the right ascension is going to be 6 hours
Very good. How did you know that?
because it's 90 divided by 15
Well,
degrees.
remember, we're doing, yeah, okay, fine. It's a big clock, right? How many hours is on the entire clock?
24.
So a quarter of 24 is 6
Right.
hours. Same
It
thing.
is 6.
Same thing that you said, right?
Yep.
Okay, so what about the declin? All right, so 6 hours. What about the declination?
Is that 23.5 like on the graph?
Yeah, it's positive 23.5 though.
Positive 23.5.
Degrees. Not bad. Okay. I like it. Let's keep moving here. So we'll try the fall equinox. Fall equinox. What y'all thinking?
Would that be 12 hours, and the declination would be 0 degrees?
Nice. 12 hours because you go eastward from the spring equinox. Halfway around the globe is 12 hours. And you're on the celestial equator, so it's 0 degrees. Cool.
Can you play that again, like you just did, please?
Yes, I'd be happy to. The trick isn't just memorizing the definitions of these angles. Let me first explain declination. Declination is degrees plus or minus from anywhere along the celestial equator. So if you're on the red ring, your declination is 0. If you go above the red ring, you go up to, well, let's do it here. You go up all the way up to positive 90. In this case, our point is on the celestial equator, so the declination is 0 because it's on the celestial equator. The reason why it's 12 hours is because we measure each point on the celestial sphere, we measure it eastward, which is counterclockwise from the spring equinox. And we measure it in a 24-hour clock. If you go all the way around the celestial equator, that's 24 hours. If you go halfway around the celestial equator, it's 12 hours.
Okay.
Our labs ought to help today because today we're going to use these coordinates to find the brightest stars in our sky. So you'll actually get to see me. We'll do it together as a class. For instance, you can see your hours of right ascension here. 17 hours, 18 hours, 19 hours, 20 hours. And notice that the right ascension, it's like a longitude. It goes all the way across. So all points on this line are 18 hours. Oops, sorry. I was trying to trace that out backwards. Yeah. Okay, let's see if that made any sense. Let's do the winter solstice. Anyone got that one?
Would it be right ascension 18 degrees and then declination?
18 degrees?
Oh, sorry, 18 hours. My apologies. And then declination would be negative 23.5 degrees.
Very good. I probably lost a few people during this exercise. Clearly a few of you understand, but I'm sure not everyone's going to. Let's just explain that one again. It's this point here. This point, if you go from the spring equinox, is 3/4 of the way around the globe. So that's 6, 12, 18 o'clock. And it's below the celestial equator, minus 23.5 degrees. Okay, we're going to practice this, and we'll practice this in our labs today. Unfortunately, I ran out of time here. Would you guys like to take a 10-minute breather before we do lab? Does everyone like the idea of just a little pause to, you know, freshen up or something? Okay. So today it just kind of worked where I could end exactly at 12:50. So I'm going to pause in a minute. You're going to have 10 minutes, and then at 1 o'clock we will begin lab 2 on celestial spheres. You should either have your lab printout or you should create those tables in your notebook with a ruler, okay? Okay, good luck. I'll see you in 10 minutes. Okay, welcome to lab. As a few of you may be confused about, I'll say it again. We do labs on Monday collectively, and we do homeworks on Wednesday collectively. Most of you who've been with me from the start know this, but a few people have been kind of casually showing up to lecture when it works for them. So you need to know that we do our lab every Wednesday. Every Monday. We're about to do lab number 2. And on Wednesday's class at 1 o'clock, we will do the homework together. Today's lab is on the celestial sphere, which I have over here right next to me on a milk crate. I'm going to see if I can connect my phone so that we can do this together. Before I connect my phone, let me start by saying a few words about constellations. I didn't get to say these in any of our lectures yet, but you may need to know this for today's lab. Hold on, let me just check the chat here, see what's happening. Okay. Noah and anyone else, if you can't watch this lab today, I'm recording it, and it'll be uploaded by about 4 or 5 p.m. And then you need to watch it and get that submitted tonight. I'm going to try to grade those labs as soon as possible. So, you know, I want those labs in by the end of the week. I want the homeworks in by the end of the week. Okay. Anyways, let's share screen for a moment. And I'd like to go back to a slide that's in our lecture notes about constellations. Constellations are more than just the stick figures that you see on the sky. They actually represent areas or territories on the nighttime sky. So you can see that Orion is a stick figure that connects these different stars here, but that there's actually a boundary. I should pick a different color here. How about green? We've actually traced out a boundary surrounding Orion, and anything within this box is considered to be in the constellation of Orion. Now, do you guys remember how many constellations there are total in the nighttime sky? Who remembers the number of constellations?
13, right?
That's the zodiac, but there are much more, like, look, Canis Minor isn't
It's
in the
8,
zodiac.
isn't it 88?
Hey, not bad. Is that Bella?
Yes.
Nicely done, Bella. 88. So that means there's 88 zones or territories on the celestial sphere. Just like, you know, if you were to throw a dart at the map of the United States, that dart would have to land in one of the 50 states. If you were to throw a dart at the celestial sphere, you would end up in one of the 88 constellations. Now, let me give you a little orientation to this globe. Let's see if I can get my phone working here. I'm going to share screen with my iPhone. Hopefully that works today. Yes. Okay. You guys see my camera, right? I'll try to not make it so shaky. Someone in one of the classes had a suggestion that I dial into the Zoom, and I may actually want to do that eventually, but for now, don't forget to put your name. This is LAB2. And don't forget to put your section, or AS1010, whatever your section is. You could be 001, 002, or the night class 101. All right, so let's just start by doing that. Okay. And what you see here is in table 1, these are the 10 brightest stars in the sky. We've been given their right ascension, their declination. Our goal is to find the name of the star and the name of the constellation in which they're located. Let's go ahead and let's orient ourselves with our celestial sphere here. I've got a cue card that I can use there for help. So let's just kind of look at a little section over here. Sorry. It's hard to do this with only 2 hands. I need octopus hands for this job. Okay, so you'll see that the stars are shown as little yellow disks, and these lines, these are the stick figures to the constellations. Hopefully you guys can hear me okay. I'm going to just, for the purposes of the recording, scroll up to me so people can see what I'm doing here. The stars are yellow. These solid blue lines are the boundaries of the constellations. The names of the stars are in black. That's Alpheratz. And the names of the constellations are in blue. That's Pisces. And can you guys see these dotted blue lines? That's the dotted blue lines are the boundaries of the constellations, okay? Now, the celestial equator is here. So lines of declination go above and below it. For instance, this is positive 10 degrees declination, positive 20, positive 30, positive 40, all the way up to Polaris, which is at positive 90, okay? And we can also go in the other direction. We can go down negative 10, negative 20, negative 30, and so forth and so on. Now, the hours of right ascension are listed here. The right ascension are kind of like these tangerine slices. 0 hours is there. Here's 1 hour. It's a little busy in here. 2 hours. You can see 3 hours of right ascension. 4 hours. And we even have these little tick marks up here to help us estimate the minutes. So let's think about this. Now, it would have been nice if they put the tick marks along the celestial equator, but they, for some reason, put the tick marks at positive 10. If we divide an hour into 3 segments, what is a third of an hour in terms of minutes?
60 minutes.
60 minutes in an hour. What's 60 divided by 3?
20 minutes.
So this is 20 minutes. This is 40 minutes. Let's see, we have 1, 2, 3, 4, 5 boxes. 20 divided by 5 is 4 minutes. So each of these little tick marks are 4-minute intervals, okay? Let's get right to it and see what we can do. Our first star has a right ascension of 6 hours and 43 minutes, a declination of minus 17 degrees. So let's go over to 6 hours and 43 minutes, okay? Hold on a second. Okay, so there's 6 hours, 20, 40, 44, but we need to start here. Well, those vertical lines are actually nice for estimating minutes. If this is 44, we want to start right there in the celestial equator, and we have to go down 17 degrees. So we'll go down minus 10, there's minus 20, and there's minus 17. What's our star?
Sirius.
Sirius. And what's the constellation?
Canis Major.
Canis Major, the big dog. Sirius is the dog star. It's the brightest star in our sky. Historically known as the dog star because it's in the constellation of Canis Major, the big dog. I may break one of my own rules and I might switch to pens so that we have better contrast here. Sit tight for a second. I think I'm gonna also, I need to kill my my display settings. Here we go. Sorry, okay. Let's move on to the next one. 737, positive 5, okay? I'm going to just keep using this cue card, so bear with me here. Okay. So there's 7 hours. 7:20, 24, 28, 32, 36. We have to start at the celestial equator. And then positive 5. What's our star?
Rossi. I don't know how to say it, but
It's Procyon.
Procyon then.
Here's a hint with pronunciations. In Latin, there were no soft C's. Like ciabatta bread, you wouldn't say that in Latin. Latin C's were like K's. So
Okay.
Procyon. And that's Canis Minor. I spelling that right? Yeah. Normally, I always do this in pencil, but I'm worried that the pencil's kind of hard to see on my phone there. Next up, 2040, positive 45. So we're going to have to swing around this globe here. Okay. Here's 20. 2040 is there. And we need to go up positive 45, positive 10, 20, 30, 45. What's our man?
Deneb.
Deneb, and the constellation is Cygnus the Swan. This star is up in your sky tonight, by the way. Deneb is the tail of Cygnus the Swan. Okay. Next up is 1948, positive 9. Let's see, here's 19. I can already see which one it is. 1948 is almost at 20. Positive 9 brings us to which star?
Altair?
Altair. And can you tell what constellation that's in?
Aquila.
Aquila, the eagle. Altair is the eye of the eagle, I think, or something like that. Aquila, the eagle. Next up, 513, positive 46. Sorry. That's 5 hours right there. 5, 4, 5, 8, 5, 12. So pretty close to that between these two lines. We got to go up positive 46, positive 10, 20, 30, 46. What's my star?
Capella.
Capella. And Capella is actually over here in, you say that as Auriga, is a herdsman. So our star is Capella. And the constellation is Auriga, the herdsman. Sorry. Too many damn things. All right. Next up, 513, same red ascension, but -8 this time. So 513 was about there. Start the celestial equator and go down 8. This star is actually, Saif is this. This is the constellation of Orion here, okay? Notice that Orion lies right on the celestial equator. That's a pretty good rule of thumb, guys, for learning your sky. Everyone knows the belt of Orion? The belt of Orion is right in the middle of the celestial equator. So keep that in mind when you're out looking at the stars. This star is the lower foot. It's called Rigel. Okay. 1410, positive 19. Okay.
Wait, what was the other one? What was the constellation name?
Orion. Rigel is the star name. Orion is the constellation name.
Okay, thank you.
No problem. Okay, now we're going to go to 1410 and positive 19. I just want to be careful not to drop this thing because it's going to be really bad. Okay, so here's 14. 1410 is just like a little bit in. Positive 10, positive 20, that's our star there. What's the star called?
Those are
Arcturus.
names. Just
They are Greek. Many of the names of stars are either Greek or Latin, or they were preserved by Arabs during the Middle Ages. So Altair, Aldebaran, they have names that are Arabic in origin. Arcturus is part of this constellation here. How do you think you say that?
Buddhist?
It looks like booties, but there's an umlaut there. It's pronounced Bootes, the herdsman. Bootes is also a shepherd or something. Okay. So that was Arcturus. And that's in Bootes. Not every day you get to make an umlaut, you know what I'm saying? 553, positive 7. Can you guys find the star?
553.
What about without my help? Can you do it?
Is it Bellatrix?
No, because this is 5 hours and that's 6 hours. So 53 minutes would be a lot closer to 6 than it would to 5. So
Sigus. Oh, I can see the whole, that one right there.
Betelgeuse, that's right. This is 553 and that's a positive 7. It's that famous star Betelgeuse in the constellation of Orion. You know, doing labs online is always a little janky in itself, but I'm trying to recreate the experience of what you would be doing in the classroom. It's never going to be the same as holding it in your own hands, but this is similar to the experience. You know, it's the flavor of the feeling. And you get to practice those equatorial coordinates. Okay, plus it's fast and easy, and we all like that. Okay, 1627 and negative 26. Let's see where we're at.
Professor, how much would you say a celestial sphere like that would cost?
These are actually, oh, this is so sad. One of the reasons I'm kind of being careful with this thing is one of these spheres cost about $500. And
okay.
They're kind of like a boutique thing that was made by like a husband and wife team, and they went out of business and they no longer make these. So I've been desperately trying to get a celestial sphere of this quality. Again, they're cast in this kind of hard plastic. It's, I don't know what you call this material, some kind of hard plastic. I'm forgetting, the name of it is blanking on me right now, but I would really like to get that team to make more of these so I could buy them, and I can't find them anymore. So I've already broken a few during my years here at CCRI, so I'm a little nervous about it sitting here on top of these milk crates. So I'm going real slow right now. But by the way, you can find versions of them online. They're just not as good. One of the reasons why this one is so good is it has this thing called the horizon ring, and the horizon ring is really nice. So you'll find them online sometimes or on Etsy. You can find used ones of these. Let me know if you see them online. I want them. Okay.
Brendan,
Yeah.
Ava's having a hard time seeing them. She wants you to put the paper behind it.
Okay. I'll try to do that. It can be a little awkward because I have to move. I will do my best, Ava. Thank you. I didn't see that in the chat, so I will do my damnedest, okay? The next one we're going to do is 1627 and -26. So this one will be hard, Ava, because it's on the other side of the globe. I don't know if you can see this of what's going on, Ava, but I only have access to the globe from that hole, and the Earth is sort of in the way. So over here in 16, we're going to have to rough it, okay? There's sort of no good way. I guess I could look through the globe, but I don't know if that's going to work with my phone. Let's try this. Let's try looking through the globe. I'm not sure if this is going to be any better. So we're at 1627. So we should be somewhere in the middle there, right? And we've got to go down 26, down 10. Oh, sorry. That's 1617 is over here, right? So 1630 will go down 26, down 10, down 20, and down 6. What's our star?
Antares.
Antares. Do you know what Antares means, Juan? It means anti-Mars. People used to confuse this star with Mars because it's red. It's Antares. Now, don't cross the dotted blue line. Let's see if we can figure out where this constellation is. Holy cow, it's in Scorpius. So that's a scorpion, and Antares is like the stinger of the scorpion. Anti-Mars, Antares in Scorpius. +39. Let's see here. So there's 18. That's 1840. 1836 is that tick mark. +39, up 10, 20, 30.
You went the wrong way, Brendan.
Oh, is it negative?
No, you're in 17.
Oh, you're right. I'm so used to doing it backwards. That was a test to see if you were following me. Congratulations, Joel. You have passed the test, okay? All right, so sorry, 1839. Yes, you're right, Joel, is right about there, okay? And now we're going to go up 10, 20, 39. What's our star?
Vega.
In the constellation?
Lyra.
Lyra is the harp. Lyra is the harp. That's right. Vega's a very famous star. Vega will appear in our homeworks on Wednesday. So this all ties in together nicely. So Vega, and that's in Lyra the harp. Oh, I'm sorry. Minus the E, I think. Did I say that? Yeah. What the hell am I doing? The reason why I put the E on is Lyrae is the plural of Lyra. So sometimes if you're talking about a binary star, you'll say beta Lyra or something. Lyrae. Okay. When you say the Hall paper, do you mean the whole paper, Ava? Or do you mean, what do you mean by Hall paper?
Yeah, that was what she meant. She couldn't see the constellations.
Is that what you want, Ava?
We're doing table 2, right?
Well, we're doing table 1 right now, but we're going to move on to table 2.
Okay.
Okay. There's the whole bloody thing for those of you who got lost in the sauce there. Are we satisfied? Okay. Now, table 2 is about the locations of the planets. That's okay. Guys, I don't see any planets on here. Why not?
They're always moving to new coordinates. They're not
Yes.
plotted on celestial
Who said
globe.
that?
I did, Rory.
Oh, hi, Rory. Yes. Rory, that's where we get the Greek word planetos from. Planets mean wanderer in Greek. And the Greeks noticed that the planets drift with respect to the background stars. Very good. So here's how this would work, Rory and friends. What we would want to do is, in the olden days, you would keep track of the positions of the planets using something called an ephemeris table. There's one that I like called ephemeris.com. I usually just type sun to Sedna. And ephemeris.com shows us the right ascension and declinations in terminal font of the 5 naked eye planets. We're going to need these for today. So they've got it. Let's see here. The right ascensions are in hours, minutes, and seconds. The declinations are in degrees, arc minutes, and arc seconds. We don't need to mess around with arc minutes and arc seconds. We need hours, minutes, and then degrees for declination. So let's just kind of jot these. Sorry, we want to get Saturn too in there. Let's get these coordinates down kind of on the side. Our goal for this section is to discover in what constellation are the 5 naked eye planets tonight. So why don't you just copy along with me here the coordinates. We'll make a little mini table. We'll do the right ascension here. And we'll do the, hold on, let me get my ruler. We'll do the declination there. I hope that's enough room. I kind of didn't leave a lot of room there. All right, so the declination for Mercury is 1249. Sorry, the right ascension is 1249. The declination is -6 degrees. Venus is 845, or 846, I guess. The declination of Venus is +17 degrees. Mars is 150 and +7 degrees. Jup is 1916 and -23 degrees. Sorry, that's pretty small handwriting there. I should have made this bigger. 1950 for Saturn and -21 degrees. Hello?
Yeah, we got you now.
Hello.
Did you guys, did I lose you for a second?
Yeah.
Yeah.
Sure did.
This is horrible because I don't know if I'm still recording, I guess. Am I here? Where am I? Oh, I'm just.
I can hear you, but I can't. Oh, now I can see you now.
I was a troll. So did I just glitch out?
Yeah.
Well,
Okay.
the audio did.
I don't know what that means for my recording, but I sure as hell hope it didn't stop because that's going to be a nightmare.
No, all the numbers showed up. We just couldn't hear you talk.
Yeah, the last thing that I heard was 1916, and then from there it cut out.
Oh, really? Oh, wow. Okay. It says recording, so I'm not going to mess with it. I'm just going to keep recording. And I pray to God that it has one file, not 2 files. Otherwise, I'm going to be in a nightmare scenario here. Share screen, iPhone. Let's see if I can fix that. Shoot.
You're gonna have to reset your phone again.
Oh God. Don't you just, I love this. This is my favorite thing ever. Oh. Yeah. Guys, you don't realize this, but the phone sharing thing, it doesn't always work perfectly. It works 50% of the time, I'd say. So we got lucky that it just worked out so well for us. Come on, come on, come on.
It never worked over the summer, Brendan.
Someone had the idea of me zooming into the class. I guess I could try that too, right?
Maybe.
Let's see if that works. That's probably, I've been meaning to do this. The problem is I need to find, where is, you know how like I send you guys the link? Well, it never shows up in my phone email for some reason.
Go to your sent box.
No, but I sent it from Blackboard, right?
You should be able to just type in the code and the password. That's what I have to do.
Oh, really? Would you be willing to read it to me?
Yeah, give me 1 second. Let me pull it up.
Wait, hold on. I can't. Can I sign in simultaneously with my?
So if you type in the meeting ID first, it's going to ask you for the passcode, and then before you just hit enter on the passcode, leave the Zoom call through your computer, and then you'll be able to join it on your phone.
Wait, I don't want to leave. I cannot leave the Zoom call from my computer, Rory, because I'm recording this, and two,
I did.
Yeah.
I put it in the message box, the chat box, the link. Check the link, the chat box.
Hold on, guys. There's an issue here. I need to figure out, can I do this? I have one. You guys all have to sign in when you do this, don't you?
Yep.
I don't think I can sign in twice from my phone and.
Oh, yeah.
You probably have to make a second account or something like that if you want to continue recording.
This is ridiculous, right? Hold on, I got a better idea. Let me just restart my phone. You know what's faster than doing that? If I cycle power on my phone, it should let me get back here. We're actually doing pretty good on time, so we're okay for a second. Just, I apologize for this bullshit. Oh, okay. Meanwhile, while I'm cycling power, this ain't gonna be pretty, but here, can you, hold on, let me get my Logitech so I can zoom this. So Logitech will let me change the focus on this so that you guys can read it. 1 second.
Is that 1950 at the end?
1950 at the end, that's right. Just bear with me here. Oh, everything is moving really slow, guys. I'm sorry. Okay. So let me focus. That's pretty good, right?
Yeah, that's good.
I'm trying to hold it steady, so. Okay. Now I'm out of focus. So, guys, let's try this again with my phone. Sorry for the whole.
What was Venus's deck? Is it -17?
Positive 17. I'm going to try to share screen again here. Enrique, creating a new Zoom account is an idea. I just don't have time to do that right now, or you guys will be sitting here forever. So let me just do share screen. iPhone. Pray to the gods. Pray to the techno gods. Come on, baby. Yes. 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 Okay. We're back, and we're better than ever. All right. Do you guys have that? All right.
Yep.
Yeah.
All
I
right.
have it.
Here we go. So let's do the first one. Let's do Mercury. Let's just call it 1250 and -6 degrees, okay? So let's see here. I can see 12. That's on the other side, so that's going to be really tough. Let's just do this one backwards, okay? So here's 12. Here's 13. 1250 is just before that, and it's -6 degrees. What constellation am I in?
Virgo.
Very good. (8:45) positive 17 degrees. So right in front of me, I have 8, and there's 9. 8:45 is about here. Positive 10, positive 20.
Is that Cancer?
That's right, Cancer. (150) positive 7. Scroll around here. Okay, there's 1. There's 2. 150 should be a few tick marks beforehand. And then positive 7 puts us right there. Now we have to be careful not to cross the dotted blue line. You can see there's a dotted blue line above me. What are we in?
Saturn.
Pisces.
Pisces.
Oh.
Got to be careful not to cross the dotted blue line. It would be a little easier if you were doing this in person. I know it's kind of awkward through my phone. Okay, 1916 -23. So there's 19. 1916 is here. -10. -23. Okay, let me spin this up a bit here. Let's try that again. So 1915, and then -10, -20, -23.
Sagittarius.
Very good. Let's try to spell this nice and careful here. SAGITTARIUS. What are you guys noticing about all the constellations that the planets are in?
That's the zodiac.
Yeah. And that makes sense because that's where the ecliptic plane is, right? This should be jiving with what you learned in class. 1950 and -21. 1950, -10, -21. It looks like we're back in Sagittarius again. We can't cross the dotted line, or the Capricornus is over the dotted line, but it looks like both Saturn and Jupiter are in the same constellation. We usually call that a conjunction or something. People who worship astrology go nuts over this kind of stuff, you know? If Jupiter and Saturn are in Sagittarius, then I don't know, you're going to get a stomach ulcer or something, you know, like who knows what it is. Sagittarius. Okay. How's that? Sweet. I'm just kind of holding it there for a second because I know sometimes people take a minute. Let me see what's popping on my chat box here. Oh, can I not look at the chat? I don't think I can see the chat while I'm in phone mode. So someone tell me what the chat says, or that I'm.
Nothing. You're good.
Okay. Maybe it was a private chat. I don't know. Shoot. Okay. Yeah, I can't. I hid the chat box, so I don't know where that is. Okay. Just a second, guys. I'm fiddling with my windows here. Fiddling with my windows. Okay. We're going to do one more bit before we end, and this is a fun bit. Solar positions along the ecliptic. We want to move the sun to these dates and then see if we can empirically determine the right ascension and declination. So check this out. One of the reasons why this globe is pretty tight is you'll notice that it has the ecliptic printed on it, right? January, there's February, and they have dates along the ecliptic, February 5th, February 10th. They even have, watch this, they have a nubby, a little nubbin up at the top, and that moves the little sun along the dates of the ecliptic so you can see where the position of the sun is on the celestial sphere. Now, the first suggestion was that we move the sun to March 21st. So let's kind of, hold on. You know what I can do? I can wrap this. Let's do something. Let's try to be clever here. Wait. Hold on a second. I'm trying to be witty here. Just a second. If I put a piece of tape at the top of this thing, like that, whoop, drop my phone, I can tape this to the sun, and now I can move the sun and you guys can see the back of it better, okay? So let's move this to March 21st. It looks like that's the 20th, and that's the 25th. So the 21st is right about there. What would you guys say the right ascension and declination of the sun is on that day?
10 degrees.
Well, if that's declination, was that Juan that I heard there?
Yeah.
Juan, remember that this is the celestial equator. Positive 10 degrees would be up there, but the degrees measure plus or minus from the celestial equator, right, Juan?
Mm-hmm.
So 10 degrees would be if it was up there.
Okay.
It's actually more like how many degrees?
9 then?
Well,
0, I believe.
if this is-
Zero?
yeah, it's more like 0.
Oh, yeah, the equator. Okay, I get it.
Do you understand? Because 9 degrees would actually be pretty close to 10. But I think
Yep.
we're actually closer to 0 degrees declination. So let's do that. And what about the right ascension?
0 as well.
Yeah. But we write that as military time. Boy, doesn't this sound familiar?
Yeah, we went through this already.
We did, didn't we? When did we do that?
Spring Equinox.
Yeah,
Yeah,
we
these
did
are the
that. I guess that was me
equinox.
trying to help the class out, right? Well, let's just kind of confirm it, but I bet, do you guys already remember what June 21st is going to be?
The summer solstice.
Right. And what's the RA and dec of the summer solstice?
So 6 hours, 0 minutes, and positive 23.5 degrees.
Let's just confirm that by eye, because that's the whole point. The whole point of a lab is to see something with your eyes that you learned in notes in class. So let's just go to June. I hope I don't lose that card. There's June 21st, right? So we're kind of at positive 10, positive 20, positive 23. The sun doesn't perfectly line up with the dates of the ecliptic because, you know, this thing isn't perfectly calibrated. But there's positive 23.5, and it looks like we're at 6 hours. That makes sense. How about the fall equinox? If we slide over to September 21st, which is here, there's September. What's that going to be?
180.
Hold on, we don't do 108. Right ascension is measured in hours. That's 180 degrees along the ecliptic. That's measuring degrees along the ecliptic. That's something else. I want a right ascension and a declination.
12 hours.
12 hours and 0 degrees.
Yeah. And then you guys can probably guess December 21st. Nah. What's our man?
Uh, 18 hours, 0 minutes, and then negative 23.5 degrees.
Yeah, it should be down here, so it's -10, -23.5. Very good.
What was the degree for June 21st?
Hold on, let me stabilize my phone. I'm sorry.
Yes, you're fine. 23.
Does that answer your question?
Yeah.
Okay, cool. What about today's date? Today is 9/14, right?
Mm-hmm.
We're actually pretty close to the fall equinox. So I bet, let's try to do one for reals here. Let's try 9/14. So something like that. So let's get real here. This is the sun. That's September 10th. That's September 15th. So September 14th should be a schmidgy widgy right over here. What would you say is the RA and what would you say is the deck of the sun on this date?
RA is 11 hours.
And how many minutes?
I forgot. Is it 4 each?
The big ticks are 20 minutes. The little ticks are 4 minutes.
So 24 minutes? Like around 24
Yeah,
minutes?
okay, fine. So we'll say 11:24. How about the deck?
Hold
on, deck is plus or minus from the celestial equator.
Plus 0.5 degrees.
Yeah, positive 0.5 degrees. I'm sorry, not 0.5, but 5 degrees, right? Because this is 10.
Oh, yeah.
This isn't 1 degree, this is 10 degrees. So that's positive 5 degrees. Do you want to see how close we, you know that ephemeris, they should give us the actual, let's see how good we came. I want you guys to use these numbers because we took them from our globe. Let's see how close we were by checking out ephemeris.com. According to ephemeris.com, 11:30, positive 3. We got 11:24, positive 5. Not bad, right? We actually we're pretty close to the correct answer. I like it. One of the interesting things about this globe is I believe this globe, I was telling you it was a husband and wife team that made it. And check out the date on this thing. The date this was made was 1967 in Michigan by the Celestial Globe Corporation. Every 50 years, we need to update the coordinates, the right ascension and declination of stars, not so much because the stars are moving, but because Earth is spinning in its axis. Not only is Earth spinning on its axis, but it wobbles on its axis like a top. Gravitational interactions between Earth and Moon cause the Earth to go through a motion called precession. Precession is where Earth wobbles like a top, And over the course of 26,000 years, Earth twists its axis into different locations in space. Basically, the motion kind of looks like a spinning top here. The motion that Earth is going through is identical to the motion. Wait, let me get my phone back up here. Oh, there's the chat. Basically, it's identical to the motion of a spinning top. So just like a spinning top undergoes precession, like so, Earth is doing this, but over a period of 26,000 years. It's kind of doing this wobble. And that actually causes the ecliptic to drift and change its position with respect to the celestial sphere. One of the fun things I love to do with this globe, and this will be the last thing that we do today, I'll just do it for a few of you, is I love to show people that because of this 26,000 year precession, whatever astrological sign that these astrology smokers tell you that you are is actually no longer valid, nor was it your actual sun sign. And the reason is because most astrology magazines and pamphlets and horoscopes, they're based off a 2,000-year-old book called Ptolemy's Tetrabiblos, published around 50 AD. In the intervening time between 50 AD, or let's say Common Era, as it's more appropriate to say, up to the year 2020, that 2,000 years is a significant fraction of the 26,000 year precession of Earth's axis tilt. And that means that the sun is shifting its position with respect to your zodiac sign. If you were born in the last 50 years, which most of us in class here are, then the sun was not in the location that they tell you your astrology sign is. And we can try this out. We'll try it out with Adam. Adam, I'm going to call on you for a second, just pick on you. Adam, what's your birthday as like a month/day?
12/11.
So why don't you go write 12/11, so you're December 11th. And now let's write, what is your zodiac sign supposed to be? If you look up your co-star or something like that. Do you know what your zodiac sign is supposed to be?
Not off the top of my head.
It's Sagittarius.
Then you're cool. Okay. Your sign is supposed to be a Sagittarius. I was thinking that. That's if you go to like astrology.com or something, right? The fact that you didn't know, Adam, actually earns you points in my book, okay? Now let's go ahead and let's look up his real sign, okay? So it's 12/11. Let's give me over here. Let's see. So the idea behind your sign, Adam, is that's supposed to be where the sun was when you were born, which was probably, I don't know, 20 to 30 years ago. Let's go over to December together. And let's scroll to December 11th. Okay. Oh, this is going to be perfect. You were the perfect person to call on. So he's supposed to be in the constellation Sagittarius, which is over here. But look, the sun has crossed over this dotted blue line, and December 11th no longer appears in Sagittarius, but it actually appears in the 13th zodiac sign, Ophiuchus. And Ophiuchus was not actually a zodiac sign when Ptolemy made his Tetrabiblos in 50 AD. So your real sign, you are the 13th zodiac sign, Adam, Ophiuchus or Ophiuchus. Let me spell that, Ophiuch. So Adam has been transformed like a chrysanthemum or something, or a butterfly. He's become the 13th zodiac sign. That's where the sun was on your birthday. So don't let anyone tell you you're a Sagittarius no more. Now, of course, it's all a bunch of bullshit, but it's interesting. Like, you know, we can try it. Juan, what's your B-day? We'll just do this for a few of you just because it's fun, and then I'll stop. Let's try Juan. What's your B-day?
12/28.
Oh, so you might actually. What are you supposed to be?
Capricorn.
So you're Capricorn. And now let's check out your real sign. I bet you've drifted into Sagittarius, but I'm not sure. So 1228, your sign is supposed to be Capricorn. Let's go to 12. That's one of the fun things about this globe here. So there you are. There's 1228. When you were born, Juan, the sun was in Sagittarius. How does that make you feel?
Oh, I didn't know that.
You are now a Sagittarius. You're no longer a Capricorn, okay?
No.
So you're going to have to start changing your personality type to match the horoscope. Let's try someone else here. Let's try, who else do I got in my, Nicole, how about you?
So my birthday is 10/4. I
10/4.
should be Libra.
So your claimed sign is a Libra.
Mm.
Let's go over here to October 4th. And where did you find the sun on your birthday?
Virgo.
Yeah. You're now a Virgo.
I feel lied to.
So is that like always going to be different?
Every now and then it's funny. So this is a party trick that I play when my friends come over and we're drinking beers and they look at the globe and they're like, what the hell is that thing anyways? I'm like, oh, I'll show you what it is. Let's find out what your zodiac sign is. And then I give them the speech, right? And usually it's a little more slurry than I'm giving to you guys right now, but it's about the same thing. And two of my friends came over the other day and they were like, well, I'm supposed to be, I don't know, a Sagittarius. And I went to their birthday and they were still a Sagittarius, Jake.
Oh, okay. So it's
and
not.
Two of them in a row. But can I tell you what happened, Jake, is some of these constellations are quite large. Like it depends which constellation it is. But Sagittarius covers many swaths of right ascension. Like, can you see how far Sagittarius goes from there to there?
Yeah.
So what happened is they were on the cusp of like Sagittarius, Capricornus, but the precession of Earth's axis had drifted them back to the cusp of Sagittarius and Ophiuchus, but they still barely made it. And it kind of ruined my point, and it made it look like astrology was real. So I was pretty bummed out when that happened. Let's try it, Jake. Let's try it with yours. Let's see if we can find anyone who actually does have the same sign. Jake, what's your B-day?
2/22.
Sorry, not Jack, but Jake. Okay, 2/22. What are you supposed to be?
Pisces.
Okay, so let's go to February 22 and let's see what's happening. I bet if we went through enough people, I mean, I'm not going to go through the whole class because there's too damn many of you for this to be fun still, but a couple will be fun. February, hold on, that's March. So February 22, right?
Yeah.
So you're here. You've drifted as well. The sun was actually in Aquarius on your birthday.
All right.
So you're no longer a Pisces. You're now an Aquarius. So what's it all mean? It means that if you have two options, if you want to keep believing in astrology, you either have to acknowledge that the sun was not in this constellation, but was in this constellation. That means the people who are telling you the horoscopes, they're so ignorant that they don't even know this, right? So there is a certain sect of astrology, by the way, which is like a new age, really new age astrology, which actually attempts to use the modern positions of planets. But most of the time, the one that you see online would be, like, for instance, Jake, you're supposed to be a Pisces, but the sun was actually in Aquarius. If I go, I don't even know what a website is, but if I go to CoStar, or if I just go to, I bet there's an astrology.com. And if I type in your birthday, let's see if they get it right. So let's go to your daily horoscope. And you were 2/22. Find out your zodiac sign. So let's see here. February 22. Let's do it right. Let's put your birthday into, what's the year, Jake?
98.
Oop. definitely don't want to get notifications from you guys. 98. Oops. Okay, let's see what they say. Ha! Ha!
Lies.
They don't even know what the hell they're doing. Hey, man, no matter how much you have planned for today, try to keep things simple. Don't toss too many details into the mix. Don't try to learn anything. Don't challenge yourself. Your brain can't handle it. It's weak. You know, like that's the kind of shit that they've got to offer you. Don't listen to it, man. It's all witch doctor voodoo bullshit, okay? So, all right, you've learned an important lesson here. And the important lesson is when they tell you what your sign is, say, I'm sorry, but the 26,000-year precession of Earth's axis tilt has no longer rendered me the sign that you claim I am. And see how well that goes over at your local bar, okay? But just keep things simple, bro, okay? Anyways, I'd say that makes for a pretty good lab here today. Let's just take one more peeks. Let's see if I can share that screen one more time here. Just a last call here for anyone who might have missed it. Sharing screen. They only let me use it once a day. It's not going to work now. Did you guys get all that? Do we need to do the questions that were with the lab? Michaela, those questions during a normal year, I would actually have us do, but that's because I can move much faster when we're all working in person. I'm going to nick these last 2 pages. We've already spent over an hour doing this lab, and I'm sure you guys are getting the zap. Also, I really need to, start rendering this video so I can get it up for the night class. I'm especially worried that might be some kind of glitch in there. Hopefully not. By the way, guys, when I was grading homeworks, another thing I noticed that some of you just kind of lazily submitted the homework sideways. Can you try to make sure that it's the right side up? Because it really does take a long time to go through so many of you. Just submit those first 2 pages, Michaela. You're going to submit, let me go to speaker view here, and let me go to Brendan. You're going to submit this page, okay? And you'll submit this page. I know not everyone got to do their zodiac sign, but that's okay. So just those 2 pages, okay? That's all I need from you.
I got a question.
Sure.
My degrees are like on one side, but they're like, can I just do it this way because the RA is supposed to be there and the degrees are supposed to be there?
Hold on. Andrew, let me go to full view on you for a second. Hold on. It took me a minute to find out who I was talking to. Okay, can you hold that up and just tell me what you got? So what are you saying now?
So my degrees my RA is supposed to be there, but my degrees end up being like right there.
That's fine, as long as they're carefully labeled, as long as they're that's your declination is labeled and your red ascension is labeled. I have no problems with that. Okay.
Right.
Okay. So that was easy.
I have a question too.
Yeah. Who else?
Matt. I submitted the homework under homework 2, and then I tried finding and you corrected me saying that I should have submitted.
Hold on. Homework 2.
Yes, because the homework 1 tab is not. I don't have it in my Blackboard.
Oh,
I only have starting at homework 2.
When did you submit? All right, so you should never submit homework 1 to homework 2. That's bad juju, right?
Right.
Okay.
Yes.
When did you do this?
I think it was Friday. I'm pretty sure it was Friday.
So it was an accident. Did I call you out on it and say WTF?
No, yeah, I mean, you called me out on it, but you told me to submit it to the right place.
But now it's gone, right?
Now it's gone, yes.
All right, so if I activate it for just a minute, can you do it there?
Yeah.
All right. So you've got, hold on, let's share screen. Since I do remember that you had submitted it, but to the wrong one, I was actually wondering how I was going to deal with this. I forgot that was you.
Can I submit it now?
I'm sorry?
Can I submit it now?
When you say it, what do you mean by it?
No, if I can just submit it now, like the homework or the lab that we just did.
Oh yeah, the lab 2 you can do now. Please, everyone should submit that ASAP. Now that you're done, you should immediately submit this to lab 2, Celestial Sphere. All right, so please do that. And Matt, we have to watch out for that. We got to make sure we submit the right homeworks to the right tabs. And that's a good teaching point for everyone. Okay, so I just made that available for a second. Can you upload that? Let me know when you're done.
Yes, I'm doing it right now.
All right.
Let's see.
Are we answering the questions on the lab as well, or just the tables? Is that all we're?
Just the tables. I don't think if we start doing the questions, we're going to be here for another hour and a half. So that one's a little harder to do remotely. So we're just going to skip that one. I think we've learned enough for the day.
Just wanted to make sure.
Yep. Just those first 2 pages are all we need.
I have the email confirming that the submission was received, but it's still being uploaded.
Okay. Let's see if I go into needs grading. Woo, you guys are getting busy. All right, Matt, I see your thing there, so that's good. So, guys, yeah, please don't wait. Submit now. Submit your LAB2 now. That would be really great. That way you don't get caught in the crossfire there. I'm even thinking about, oh, you guys are having fun. Hey, Yin Chen, you look like you're having a good time over there. Other questions? Any other questions? Okay. So, guys, I'm gonna stop the video now. Okay, that's fine, Ava. Take care. I'm gonna just close this chat. I'm gonna stop the recording.